I'm really delighted to have here Zubin Jacob. Professor Jacob is a professor at the University of Purdue. He's a good friend of mine and is a very active scientist working in so many fields. And he was in Alberta first, in Purdue, then Alberta, then moved back to Purdue. We are closer now as in our research fields have some overlaps, but as he will show today, he is doing many things. And he had many, let's say, awards and honors. I have a long list here. I cannot go through this, but one of the last one is the Leopold Felsen, which is a fantastic award that he received in 2021.
Yes,
right?
Yes. Thanks,
in 2021, and it was a pleasure to hear this. But also he had an NSF career in 2017, the Purdue Seed for Success Award 2017, and so on and so forth. There is a long list here, all very interesting. So the floor is yours, and thank you for being here.
Great. Thank you, Pino. Thank you, everyone, for coming to my talk. I really cannot remember the last time I gave a talk in person. I mean, other than teaching, we are now back to teaching in person, but I don't remember. So I'm super happy to see all of you. I want to talk about two topics today. I'll try to keep it, say, within 45 to 15 minutes, and so that we leave time for questions. And I want to talk about the stuff that we've been working on in the last few years, but I would say in the last 1 year is when things have really come together. So the two topics I want to talk about is one is topological electrodynamics, and the other is the spin of electromagnetic waves, the spin of electrodynamics in matter. So before I start, I mean, I should acknowledge that everything I'm presenting is all work done by my team. Very broadly speaking, we like to work at the interface of quantum optics and materials physics. So we enjoy understanding materials from first principles and like some basic ideas, but we are always looking at the electrodynamics of materials and inspired from really the field of quantum optics. So that's very broadly how we think about the group. Let me see if there's a message here. No? Okay, all right. Yeah, I hope you can see this. Okay, so these are the research scientists and postdoctoral fellows. These are the PhD students. I will only give you kind of a sampling of the work that is being done, but you can go ahead and look at the website for more details. So let's see, is this having trouble going ahead? No, it's perfectly fine. So I'll have the talk in two parts. So maybe by around 1:20 or 1:25, I'll kind of wrap up this part one, which is the topological electrodynamics part of the talk. And here, this part of the talk is theoretical. So I'm really talking about the theory work that we have done, but I'll tell you about the experimental consequences of the theory. So we will start slow. We will start with two concepts. And from the theory ideas, if I'm able to convey these two ideas, then I mean, I consider myself successful in this talk. So I've been able to kind of convey these two ideas. Now, this would take around 10-15 minutes, but the applications of the theory are what is most interesting. And these are applications to real materials. I'll talk about the hydrodynamic fluid in graphene. So when you have interacting electrons in a two-dimensional material, in the presence of a magnetic field, you can have some very interesting phases of matter. And that is the first application of this theory. And I'll tell you about some of the experiments that we believe can be done to kind of test the predictions of the theory. And the other application I want to talk about of the theory is just applying it to a material that we all know. And that's, in this case, is silicon. And let me see if I can kind of move this thing at the bottom, because I think we can't see this. Let me just see.
You might have to go to the screen and do more and hide it.
Yeah, okay. I don't have
I'm not sure if it'll work.
Oh, yeah, okay.
Hide it.
It doesn't have it like that.
No.
Normal computer does.
The participants on Zoom won't see that though. So.
Oh, they won't. Okay. All right. So here you'll see, oh yeah, awesome, thank you. So here the theory predicts that there are some interesting atomistic waves inside even silicon that we could probe to test out the theory. So that's the first part, or the theoretical part. And then I want to talk about no, I in this case, I completely mean electrodynamic waves throughout the talk, yes. We will come to that. What I mean by that is in a macroscopic theory, such waves are not predicted. Only when you take into account the atomistic property of silicon, including the kind of lattice structure, the Brunel zone, and transverse versus longitudinal part of the dielectric constant, there are some additional waves that are predicted by this Maxwell Hamiltonian. Yes. So that's the first part. And then I'll go shortly through some of the experimental work. The spin of the electromagnetic field has not received as much interest or as much attention that it should have over the years. So I'll talk about some of the experiments which kind of point that this is a very interesting degree of freedom to start exploring for practical applications, as well as interaction of the spin angular momentum of light, because it's so it is a local quantity. It can interact with many interesting things like, say, spin qubits. So I'll talk a little bit about experimental work in this part 2, and this is probably 15 minutes. So, I mean, when you look at, say, quantum optics textbooks and so forth, they'll tell you a very fundamental concept is that the light fields are governed by, say, Maxwell's equations, which you can write in a special form that shows the symmetry with the Dirac equation. The Dirac equation governs the dynamics of, say, the electron wave function. Here you have a superposition of the electric and magnetic fields. This is known as a Riemann-Silberstein vector. And you can actually write down the Dirac Hamiltonian and Maxwell Hamiltonian and show that there's actually a very interesting symmetry between them. So this type of a theory has been kind of studied in a lot of detail all the way up to the 80s to kind of show that in free space, this is kind of the three-dimensional free space. And you can look at the Hamiltonian and you will see that the two forms have striking symmetry. In this case, what you have over here are the Pauli matrices, sigma x, sigma y, sigma z. This tells you about the spin of the electron. And kx, ky, kz is just the momentum of the electron. In the photon case, you actually have this capital Sx, Sy, Sz operators. These are also spin operators of light, and kx, ky, kz is actually the momentum of light. So this starts showing you a lot of interesting symmetries. And one thing that is captured by studying this Dirac-Maxwell symmetry is the fact that the commutation relationships for the spin operators show that in the Dirac-Hamiltonian, you have spin half symmetries. But in the Maxwell-Hamiltonian, as you would expect, when light is a boson, so the spin has to be an integer, you actually see that you have this commutation relationships that correspond to this SO3 symmetry. So this type of a theory has been studied in a lot of detail, and this is a technical aspect for the experts. One of the operators that comes out of this theory is the time reversal symmetry operator that tells you like what are the various symmetries this Hamiltonian obeys. And this time reversal symmetry is a discrete symmetry. And in the case of the fermion, because of the complex nature of the wave function, you can show that this time reversal symmetry operator squares to -1. And in Maxwell's equations, we are dealing with real fields. The time reversal symmetry operator squares to +1. And that's actually inherently related to the fermionic and bosonic nature of these fields. So this is a way of trying to understand the symmetries and asking questions. But you have very interesting phenomena with Dirac Hamiltonians. Can you start seeing interesting phenomena with Maxwell Hamiltonians? That's kind of the first half of the talk today. So what is the one success that is actually known in the field from the work by Michael Berry and many others in say, the 80s was that you can understand these two Hamiltonians and start looking at the dispersion relationships. So dispersion relation is just the relationship between energy and momentum. Now, what happens when you look at the energy and momentum? Let's look at three-dimensional space. And let us, for the sake of discussion and for the sake of symmetry, consider that the fermion has no mass. So you take a massless fermion in free space for the sake of discussion, so that way you can start seeing the symmetry with Maxwell's equations. Now, we all know this is something that you study in undergraduate curriculum, that, I mean, you have linearly dispersing light waves in vacuum in 3 dimensions. You have a momentum vector on the x-axis, you have the energy or the frequency on the y-axis, and you have linearly dispersing states in Maxwell's equations. Now, even in the Dirac-Hamiltonian, once you look at the zero mass limit in 3 dimensions, you will see that you have a momentum axis, frequency axis, and this linearly dispersing states, right? So you've probably seen this in the context of, say, graphene, massless fermions near the Dirac point. You can have these nice things. So there are some nice analogies to be made there, but this is a problem which is just the 2 Hamiltonians in vacuum. So this is so similar. The question to ask is, what is different in these 2 Hamiltonians? Now, it turns out that in momentum space, this is, remember, we are looking at vacuum, but the image that you see on the screen right here, these 2 images, this is in momentum space. This is reciprocal space for the waves in free space. Now, in that, you can show that sitting at the origin in here, there's actually a source of flux, source of a phase. And that is actually can be directly mapped to a magnetic monopole in momentum space. That's what is kind of interesting in this theory. And then the crucial difference between these two is the fact that the charge on this momentum space kind of monopole sitting here, this is half integer for the Dirac case, and it's actually an integer charge, for the Maxwell case. This type of half integer and integer difference in the monopole is actually one of the successes of studying these symmetries. And it gives you more insight on what's going on. So when we started looking at this problem in detail, we found this kind of analogy very interesting. And we said, now this is all in vacuum. Let's try to apply this theory to a practical material. And let's try to ask, we have so much insight from the Dirac-Hamiltonian. Can we generate some new insights from the Maxwell-Hamiltonian? That's really the question. And then we try to apply it to the Maxwell-Hamiltonian to materials. And in this case, I'm going to now focus on 2-dimensional materials. This is the case which is more tractable and easier to start with. That's why we started with this problem. So even before we go into all the details of kind of these things, let me just give you a flavor of the answer itself, because that's going to help understand the theory better. So the previous slide that you saw with kind of photons, say, in vacuum, and you have linearly dispersing states, this is completely no mass effects at all of any nature. But what is interesting that comes out of the theory is that when you look at the 2-dimensional case, you can actually define an effective photon mass very similar to the way you define an effective Dirac mass. So how do you do that? So in this 2-dimensional case, you have the Dirac-Hamiltonian. It consists of these Pauli matrices, sigma x, sigma y. There's a dot product. And so there's a kx and ky. This is the momentum. And then you actually have a effective mass for the Dirac-Hamiltonian that multiplies with your sigma z operator. Now, this is extremely well known, and it's very widely used. So what we did was actually think of an analogy with the Maxwell case and show that you can actually have an effective mass term in this 2 dimensions, which has the exact same symmetry as this case, as the Dirac case. So this is right here is the photon kind of effective mass. That's what M effective PH stands for. Now, what is the consequence of that? Well, the consequence is interesting. In the Dirac case, when you have the massless fermion and you add this effective mass term, what happens is 2 very crucial things. One is the bands get a sort of curvature. This is just a cartoon, so I'm trying to, and this is not the exact curvature that happens, but this is how you should think about the physical effect. And the other thing that happens is a low frequency band gap opens up in the spectrum of waves in momentum space. That's what happens when you add the mass to the Dirac Hamiltonian. Now, in the photon case, an exact analogy happens, and that's kind of explained in some of our papers, is that you have this Maxwell linearly dispersing states, and this is, now you start focusing on a two-dimensional material. If you did have such a photon effective mass, then you will have a curvature to the bands, but along with this curvature, you are going to have a low frequency band gap. And these two things are exactly analogous to each other. So that's why we called it an effective photon mass term. And then the question becomes, this is right now just a parameter that enters the theory. What does it physically mean? So through this analogy, you can show that physically, the quantity that enters as an effective mass is actually a physical response parameter of two-dimensional matter. And the response parameter is essentially the Hall conductivity. The Hall conductivity is a response of two-dimensional matter in the presence of a magnetic field. And it tells you how the X and Y currents couple to each other. So there's a X direction and Y direction. You can think of, say, the fields and which cause some currents, but there's going to be a cross coupling between them. And that can be connected to what is this quantity known as Hall conductivity. Now, so I'm giving you kind of a bird's eye view of what comes out of the theory. And so this was interesting, and we found that, okay, this analogy is nice, but then what can we do with this that is completely new? Because the band gaps itself, I mean, you can think of it, it's a trivial band gap. There's nothing exciting happening inside this gap that you have created. So looking a little ahead, we realize that your photon mass need not be some constant parameter. Your photon mass, which is an effective mass, it can actually start dispersing and have different waves, have different effective masses inside your two-dimensional material. So think of it as a dispersive photon mass. And this is, say, a case of a simplistic dispersion that we have taken just for illustrative purposes here. This has a square dependence on the momentum. Now, if you take this dispersive photon mass, something interesting happens. Your Hall viscosity, the Hall conductivity also has a spatial inhomogeneity, non-uniformity. And you start seeing what is known as, in technical terms, Hall viscosity. So in a two-dimensional quantum fluid, two-dimensional material, you can have a stress and strain response of this two-dimensional material. But in the case of I mean, physical shear and stress you can think about, but here we are talking about a kind of a quantum fluid. So you're really thinking of shearing the wave function. That's kind of the way you think about it, the stress and the strain response. And you try to ask the question, in a magnetic field for a 2D material, what are the different types of viscosities possible? Once you have the conventional viscosity, this is just telling you that if there's a rotational property to the fluid, inside this you start trying to create this rotation, that the fluid is going to try to oppose this motion. That's the very standard concept of viscosity that's known as shear viscosity. So think of it this way, your honey does not flow as easily as water. So there's a sort of friction between that, the inter layers that's causing the honey to slow down. And that's really coming from shear viscosity. It's a dissipative form of energy being lost. In a two-dimensional material, when you look at the electron fluid, you can actually have a different type of viscosity. And that is known as Hall viscosity. So let's see, the movie is playing right there. So you can see right here that the fluid is trying to go this way. but the response of this matter is actually in a completely orthogonal direction than the conventional shear viscosity. So this is actually non-dissipative, and this has been kind of introduced in the context of quantum fluids before, but we pointed out that this Hall viscosity directly connects to the photon effective mass inside this two-dimensional material. So our goal becomes trying to kind of look at the Hall viscosity in more detail. This is a response of matter that couples to the electrodynamic field in a very non-trivial way. So I'll just kind of have this one slide for the experts. I think it's kind of a very technical question to ask about is that if you have a photon mass, you can have two different ways of looking at it. One is known as kind of modifications to Maxwell's equations, known as the Procca equation. That actually breaks gauge symmetry. In our case, what you have is a Chern-Simons theory where the gauge symmetry is preserved, and your photon mass that we are talking about is a gauge invariant photon mass. And so this is the conventional kind of gauge field in say QED. You would have a gauge field that is coupled to say, this is the Chern-Simons term, this is the field strength tensor, and this is a sort of viscous term that is coming from the longitudinal degree of freedom. So what this implies is that looking from the waves point of view that we have been looking at before, the low momentum waves, electrodynamic waves in this two-dimensional material have a different commutation relationship than the high momentum waves inside this medium. So that's kind of the key insight. And there's a sign change of the photon effective mass. Low momentum waves see a positive effective mass, and high momentum waves see a negative effective mass. This is what leads to interesting effects. There are many other things you can study, but this is the case where the photon effective mass changes sign is actually the most interesting case. So where can we apply the theory? We decided to apply it to the top field of topological photonics and topological electrodynamics. There's a lot of work. I cannot do justice to this entire field in a short talk. One of the things that we are focusing on is actually the atomistic response inside materials. So instead of like texturing and studying the periodicity at a macroscopic scale, think of the theory that I'm presenting as a way to apply it to atomistic materials. So it's a U1 gauge theory that shows the gauge fields are coupled to the charges. So the focus of today's talk and much of our work is really in this regime of atomistic crystals. So what's the first system we applied it to? We try to calculate and show the atomistic susceptibility of a hydrodynamic fluid. Now, if you have kind of electrons, if you treat them in a regime where you turn off the electron interactions and start looking at like a hopping between, say, in tight binding models, you can get certain susceptibilities. But what happens in the case of strongly interacting cases, you have to have models which are a little advanced or different. And in this case, the hydrodynamic model is one of the cases which has shown a lot of experiment and theory agreements for the case of graphene. So let's now apply this model that I kind of spoke about with photon effective masses and so forth. Let's apply it to a real material. So we've kind of gone through the theory part, and now we're going to start talking about applications of the theory. So first, what you do, you have your graphene lattice, and you only look at the frequency ranges close and near this band gap frequencies that I'm talking about. So there, the electrons can be approximated by a hydrodynamic model. Like a Navier-Stokes model for low momentum waves, you have this hydrodynamic electron flow. Then what you do is you apply a magnetic field. So when you apply a magnetic field, there's a sort of symmetry which is broken of left and right going waves because you have applied a magnetic field, you have a Hall effect. Then you calculate for this hydrodynamic model, you calculate the transverse response of this charged viscous fluid to photons. In other words, this is your susceptibility tensor. This is the frequency dependence of this hydrodynamic model, and this is the momentum dependence of the hydrodynamic model. So the experts would notice this as a non-local response. But along with the non-local response, you have to really separate out the transverse response to photons and the longitudinal part to charged particles. So these are the two responses, then you put it together and you get this atomistic susceptibility tensor. So this atomistic susceptibility tensor is what goes into the Maxwell Hamiltonian. So once you have this model, you take the atomistic susceptibility tensor and look into put it into the Maxwell Hamiltonian. I'm going to come back to this kind of technical point. Let me just skip this for the time being. I'll come to this technical point in a second. But let's actually just look at kind of what comes out of doing that. So when you take your atomistic susceptibility tensor, put it in your Maxwell Hamiltonian, you essentially have this system. It has a Navier-Stokes equations. There's the Hall viscosity. There's Maxwell electrodynamics. There's sort of boundary conditions that minimize the action. And then you have the experimental parameters that are taken from some very nice experiments recently from Andre Geim and Marco Polini related to Hall viscosity and graphene. So when you do that, you actually see something interesting happening, that there's a bulk band gap. That means that waves do not propagate the bulk at all, but within the edge, the electrodynamic waves are all propagating in one direction. So it's unidirectional waves creeping along the edge, and you're actually seeing a sort of circulator behavior here. And these are really charges coupled to the electrodynamic fields. So this is a coupled system. And these are also backscattering immune, because there's actually no wave that propagates in the other direction at all. The waves can only propagate in the front direction. And this is all because the bulk has a band gap. Like I told you, the photon effective mass, the bulk, there's no waves allowed. But on the edge, there are waves allowed that only travel in one direction. And this is really part of the topological hydrodynamics and edge waves. So why do we use this word topological? Right? And that's a very crucial and technical question that I'll answer before going to the other part. So let's kind of answer the question, why do we call this a topological response, right? Now, the atomistic susceptibility tensor, we all have studied this in one form or the other. When you study like, say, optics or condensed matter or Green's functions, I mean, these are all very related quantities. There's an energy dependence and a momentum dependence to a response function. Now, if you look at a conventional system, which is on a lattice, the lattice has a very special periodicity that allows you to define what is known as a topological invariant. So think of this as a two-dimensional material. This is the reciprocal space, Qx and Qy. It's periodic. So now, if it's periodic, that means these two red lines can be mapped onto each other. And the two blue lines on top can also be mapped onto each other. So what you do is you fold this 2 times. And let's see what happens when you fold it twice. You fold it once, you get a cylinder. So all you did was take the red lines and fold it into each other because of periodic boundary conditions. Then what you do is it's periodic in both directions. So you fold it again, and what you get is the donut, or you get a torus, right? And now on this closed system, you can start defining a lot of interesting quantities. In particular, you can start asking what happens to the wave function of the electron field on this closed manifold. And the geometry of the electron wave function is what governs the topology. Now, this is actually something that is known, and I'm sure you've heard talks about the topology of Chern insulators and quantum spin Hall insulators. The case that we are studying is actually fundamentally different. Because we have an interacting electron field in the hydrodynamic model, in the hydrodynamic case, there's no simple periodicity that allows you to define a donut. In our case, and this is also a technical point, your closed manifold is extremely non-trivial. And the subtle detail is that the Hall viscosity, the same thing I told you before, the viscous response of the fluid, allows you to take the two-dimensional momentum space and close it into a sphere. All the four edges here, they actually all have very similar responses in the large momentum limit. And that allows you to really define the entire theory and all the parameters in a closed manifold, which is actually this sphere S2. So you really compactify this two-dimensional rectangle into a one-point case. And then one more technical detail that happens is that you are looking at frequency responses as well momentum responses across a very broad frequency range. Here, Kramer's chronic relationships are very important, and that allows you in frequency space to really take from -infinity to +infinity. That becomes really a circle. So your compact manifold, and this is really for the technical experts, is this S2 cross S1, which is very different from a donut. And the topology is telling you about the properties of the electrodynamic field on this closed manifold. And so this is what we call as an optical N invariant. You calculate the N invariant using atomistic susceptibility tensor and try to ask what are the properties. For any conventional material, if you try to calculate what this optical invariant is, most probably it will be undefined. That means you just get like gibberish. For the case, the special case I told you about this kind of photon effective mass and band gap, you'll actually get the number 0, which is which is essentially a trivial band gap, traditional insulator. For the case that I spoke about where the Hall viscosity exists and the photon mass changes sign, you will see that this optical invariant is not undefined. It is not 0. It actually takes this value 2. And this is an integer that tells you the global properties of the susceptibility tensor. And in that case, you will see that you don't have a trivial band gap. You have a band gap in which a special edge state emerges, and there's only one direction to this edge state. There's no edge state at all. So at this frequency, there's a wave that is confined to the edge, and it only goes in one direction. So that's really this topological case, and it closes the band gap. This is extremely crucial, that what the topology tells you is that even though the model itself is derived under many assumptions, in reality, this number is robust to a lot of perturbations. This quantization implies that even though in experiment, you will be looking at a much more kind of complex systems which will be away from this low momentum limit that we have been studying, this band gap will remain closed even in experiment. That is really the prediction. And the band gap is not going to open up for simple cases of impurities. There will be, for very hard driving, it's true that you will open up the band gap, but not for a very large class of perturbations. So what topology tells you is that this system exists in a different phase of matter than this system. And the key parameter or sort of order parameter that differentiates this phase and this phase is that integer. N equal to 0, it's this phase with a gap. N equal to 2 is a bulk gap with an edge which closes the gap. That's what is meant by this topological hydrodynamics. We have an experiment that is possible to be done. I mean, I'll skip this, it's part of the paper, but I'll skip this for the time being, and I'll just use maybe, say 10 to 15 minutes more to talk about the silicon and the other details. So I spoke to you about this Maxwell Hamiltonian. I spoke to you about the concept of atomistic susceptibility tensor. The first application I told you about graphene's hydrodynamic fluid, and I told you about the optical invariant. Let's try to now apply it to a non-topological system. Let's try to apply it to silicon. So here, I'll just talk about the answers. What we are really trying to say is that with all the tools that exist now and the tools that we have developed, putting all of these together, for example, I mean, in Pino's group, they're working on, say, first principle simulations of materials and studying them with yields. You are really starting to probe. One is the macroscopic response. This is something we understand. And I think the field has really come to a frontier where a lot of this science is really transitioning to technologies. And now we are in a position to ask the next generation of questions, which is really what is happening at the sub-nanometer level. What is really happening to the electrodynamic fields in this regime? We are starting looking at this atomistic response. So we think that this kind of regime of picophotonics is very important, and we have the tools to make experimentally testable predictions now. Now, I won't go through into the details again. This is for the experts about how we do it. So we start from the atomic lattice of silicon. We find the electronic band structure. There are many methods. In the start, we have used the pseudopotential method because it's more convenient. Then from there, we evaluate this atomistic susceptibility tensor, the one thing that I've been talking about quite a bit. This is over here, but the atomistic susceptibility tensor also has frequency dependence, momentum dependence, as well as the lattice symmetries inbuilt. Then we have the atomistic Maxwell Hamiltonian, not the Schrodinger Hamiltonian or the Dirac Hamiltonian. We solve the Maxwell Hamiltonian, which is a nonlinear eigenvalue problem, and solve for the modes predicted by this Hamiltonian. And this applies, of course, to the electrodynamic waves inside silicon. And this is one of the early results, and we've refined it considerably over the last 1 or 2 years, is let's look at the textbook prediction, right? So this is what you would see in a kind of macroscopic local textbook prediction. You can pick up pretty much any optics textbook and get this figure that if you take silicon, there's going to be a band gap. And if you go very high above the band gap, I mean, you will start seeing a sort of light line. There's a light line below the band gap as well. And that's kind of the traditional model of silicon. You will have a special kind of a mode that is possible near a macroscopic frequency, which is related to a plasma frequency that you can define even for a semiconductor. Now, this model is the traditional model, but in researchers over the years, especially in nanophotonics, have developed what is known as a non-local model of matter. And in the non-local model, you see that there's qualitative agreement, but quantitative disagreement. That is to say that you will have a branch which is not flat like this, but the branch has a curvature, and then this branch kind of goes in. So at certain energies, you'll have this additional branch that is bent in the macroscopic non-local model. Now, what I want to talk about is that away from this nanophotonic model, if you start looking at this picophotonic case, where you have the atomistic non-local behavior along with the Maxwell Hamiltonian, we definitely reproduce the macroscopic non-local case. There are some qualitative differences, but some quantitative differences, but there's one fundamental qualitative difference, and that is the existence of this additional branch. So this wave will not exist. The red branch that you see actually will not exist unless you have this atomistic symmetries included in the Maxwell Hamiltonian. So we are working on this extensively. One of the things you will notice is that for the system we have chosen, silicon, in this range, there's also going to be a lot of damping. This is above the band gap, so suddenly there'll be interband transitions and damping for this red curve. But we have kind of analyzed it in detail and shown that you can have such waves even at below the band gap. So that's the latest result, and this is work in progress. And we feel that it should be possible to start probing such waves which are originating from the picophotonic regime in the sub 1 nanometer of physics inside matter. So, so why are we excited about this, and why are we pursuing this? The thing is, we have looked at just 2 materials right now. Both of them, both graphene and silicon, is based because of the fact that these are the these systems really have very nice symmetries to work it out. But once we feel that we can prove experimentally that these things indeed work, I mean, I like to tell my students that, and the fun has just begun, because thousands of materials should be possible to be analyzed using this same approach, and we should be able to discover some very interesting insight. The 2 insights we believe we have kind of developed through this approach. One is the optical N invariant that I told you. It's a topological constant that captures the atomistic response of a hydrodynamic fluid. And the other is this atomistic waves, which we believe definitely exist in silicon. The above the band gap is what I showed the calculations for, but this damping is going to make it very difficult to observe. But we've seen some of these things below the band gap as well. So with that, let me just take maybe 10 minutes more to talk about this part 2. This is going to be short. I just want to talk about the spin angular momentum of light, which has not received the level of interest and excitement that I believe it should. I hope to convince you with some of these experiments that we are looking at. Now, what we are used to when we talk about kind of the spin angular momentum of light is really this picture. You have a plane circularly polarized wave traveling in vacuum, and you have this electric fields which are really twisting around along this axis of propagation. And so you have a spin angular momentum vector that is pointed along the direction of momentum. That's what you mean by the conventional concept of polarization. And this is really global polarization. It means no matter what point you look at in free space, you always see the same vector pointed in the same direction. But once you have these evanescent waves, nanophotonics, or the picophotonic regime, you can have the spin angular momentum take on very complex textures, directions, and values compared to the standard global polarization. And in this case, this is the case of a dielectric and air. This is the kind of case of total internal reflection or surface plasmon polaritons. Your momentum is pointed along the interface. You have a decay axis. And this is the spin, which is perpendicular and locked to the direction of the momentum. So this is spin momentum locking, but now this is not for electrons, but this is spin momentum locking of evanescent waves for photons. So this is the lock right here tells you the spin and the momentum are 90 degrees to each other. This is very different if you compare with your conventional global polarization. This is certainly very different. And in the case of, say, twisted light beams or Bessel beams with orbital angular momentum, you can have a very interesting texture to the spin angular momentum as shown right here. So this is for the twisted light beams. So if you look at the spatial distribution of light's properties, we are used to thinking about the orbital angular momentum, but these are actually larger than the wavelength. These are properties that are defined larger than the wavelength. You can define an optical chirality, which is the property of the light field that couples to molecules. And this is roughly at the size of the wavelength. But if you start looking at ultra sub-wavelength properties of light field, the spin density is actually the key property that couples to matter as well as couples to other quantities like ultra small emitters as well as spin qubits. So I want to talk to you a little bit about this electrodynamics and spin coming together for some interesting applications. So the first experiment that we performed, and this was in collaboration with Hubert Kerner's group in Germany, we looked at the surface acoustic wave. So let's see if this movie plays. All right, so I guess maybe I'll just escape screen and see if I can play the movie. Yeah, I think it may play in this case, yeah. Great, so I hope you can see that this is a surface acoustic wave. This is an interface. And as the surface acoustic wave propagates, this is the displacement of the physical displacement of the interface between lithium niobate and vacuum. So the acoustic wave changes the stresses on the surface of the material. This thing right here, it's a little small, but I hope you can see it, is what happens to the electric fields on the surface. These electric fields are actually, this will be much better. So now you can see it. You can see that the electric fields right there have an interesting tumbling motion. And that is the angular momentum of the electromagnetic field, but this is local angular momentum. And the vectors that you see, the vector one pointing out of the screen and one pointing in the screen, that's the spin angular momentum vector. So this is for the surface acoustic wave. And I think now you've seen the movie. Let me go back to full screen and then tell you about the experiment. So to probe this phenomenon, The experiment that was done in Germany is that you have a nanowire system, a quantum well nanowire, which is placed on lithium niobate, and a surface acoustic wave is excited. The surface acoustic wave goes and interacts with the nanowire. And then what you do is that you study the spontaneous emission from the nanowire as the surface acoustic wave passes through the nanowire. So what happens is that as the surface acoustic wave propagates through this nanowire, the charge carriers inside the nanowire, which are optically excited, they perform a tumbling motion as well along with the electric field. So when the electric field is over here, this is where the charge carriers are. When the electric field is here, the charge carriers move. And as the electric field rotates, the charge carriers actually move within this three-dimensional quantum well. And now if you study the spontaneous emission, you will see that the spontaneous emission signal is not only modulated with the surface acoustic wave, but there are these peaks and troughs which are actually connected to the tumbling motion of the electrons. I'll be happy to kind of talk to you in more detail about this exact experimental result. Here I want to give you a picture of kind of what are the ways of probing this spin angular momentum. For the surface acoustic wave, the nanowire is one excellent system. Now, another way of looking at this spin angular momentum of light is actually making it interact with a spin qubit. So this is an experiment done in my lab. This is work done by my student, Farid Kalor, and my postdoc, Liping Yang. So here we have an AFM tip. And on the AFM tip is actually a single NV center. This is a defect center in diamond. Now, what you do is that you come up with, go and kind of shine a detuned, circularly polarized light beam on this single NV center. Detuned because you do not want any absorption. You're looking at a coherent interaction between light and the spin qubit. That's what is shown here. This is the target beam. You want no absorption. Diamond is transparent in the visible. So you go detune and then you look at your NV center. So what you do is that when the light interacts with the single spin qubit, you actually shift the energy levels slightly. This energy shift actually changes the phase of the qubit. And that change can be read out, and you can prove that the spin angular momentum vector that I just spoke about, the energy shifts are proportional to this S vector, which was the spin angular momentum vector that I've been talking about. So we did this theory and we figured that this can actually work even at room temperature. It's a coherent interaction. It's a tough measurement, but these energy shifts can be read out at room temperature. And so let me just show you kind of the evolution. I don't know if this movie will play. Oops, I'll have to kind of escape again. Oh, just when I did the thing, it popped up. 1 second. Oh, there it goes. So think of it this way, that the movie is really telling you what is happening to the qubit. So the first and foremost thing to look at is there's a Bloch sphere. And on the Bloch sphere, there is a vector. That vector tells you the quantum state of the qubit. Now, what you do is you shine microwave pulses to rotate the vector, and then you actually transfer the phase of the qubit into the population difference. And the population difference can be read out through fluorescence measurement. Now, with that, you can actually study what happens to the level shifts. And the level shifts can be thought of as a pseudo Zubin shift, which is coming from the application of the light beam. That is why we have measured it in kind of units of nanotesla. So it's an effective magnetic field that is causing this level splitting. And this effective magnetic field does agree with experiment. And there's nanotesla fields that are created. There's a theory and experiment showing that what the phase is of the qubit coherently is actually being controlled and is coupling to the spin angular momentum line. So the final slide in my talk, and that'll leave maybe 5 minutes for questions, is that we are doing the same spin electrodynamics, but now we are doing it with completely incoherent radiation. And you can show that even if you had heated objects, if you controlled the uniformity of the heat, the temperature gradient, the equilibrium versus non-equilibrium, the structure, you can actually impart angular momentum to the thermal radiation. So very recently, we have some experiments that prove that this spin angular momentum can be imparted to thermal radiation and it can be non-zero. This is just some of the theory work showing that if you had a hot antenna and cold antenna kind of in the near field interacting with each other, the thermal emission can almost be like unity purity of right circularly polarized light. So that means the heat coming up at a specific frequencies would all be rotating and carry spin angular momentum. This can have some interesting applications as well. So with that, I'd like to conclude my talk, and I'll give you kind of a summary of the part one, which was the theoretical part, but we think there's going to be a lot of interesting developments that can happen in this picophotonic regime, both from a topological materials point of view, but also new insights on existing materials. So with that, I want to thank the audience and especially Pino for the invitation, and I'll be happy to answer questions.
If there are questions, yes, please. So I'm sorry I lost you kind of a little in the beginning. Okay. But you told us that a whole conductivity produces an effective mass for the photons.
Yes.
Can you give us a bit more? And then you told us next that actually effective mass is dispersive.
Yes.
Can you give us a bit more of a feel what's going on physically, why that is?
Okay, so first thing I'm happy about is that, what you said is exactly what I was trying to convey. So I'm happy that we're both on the same page. And now we can go a little bit to the intuitive part of what's happening, right? So in the case of the electrodynamic waves, right, the real experimental observables are all really connected to a sort of dispersion relationship. The energy and momentum of the photonic waves, which are coupled to the two-dimensional material or quantum well, 2D quantum well, two-dimensional electron gas. Think of it this way. Now, what you would do is you start studying the energy and momentum dispersion, and you would see that for some frequencies, there's just no waves allowed inside the medium. No propagation of waves are allowed in this two-dimensional material. This lack of propagation is something that you kind of know from, say, photonic crystal band gaps, right? If you say, right. But this now is at the atomistic level. There is no texturing at all. This is just a two-dimensional electron gas. You have not textured or made anything on it, but you have a band gap. That band gap has to be understood as really an effective photon mass that is coming from the coupling of the charges to the electromagnetic field. Now, this band gap itself is, it's in the technical language, it's called a trivial band gap because there's nothing interesting happening inside the band gap. But now, if you're a Hall viscosity, and more specifically, like the technical thing is repulsive Hall viscosity, and we can discuss that later. This is the spatial dispersion of the Hall conductivity. Think of it this way.
So this viscosity, that comes from the electron-electron interaction.
Yes.
Okay.
Exactly. Exactly. Now, that viscosity changes the band gap in a very special way. It's not that the band gap changes just in some qualitative numbers. The band gap closes, but it closes only at the edge. That means there's an edge wave inside the band gap. The edge wave only goes in one direction and it's robust to perturbations. So we also enjoy the engineering aspects of this. So one of the things that we thought about is, you can build a circulator which is extremely small. Normal circulators can be very bulky. But now these waves and the bandwidth can also be very, very large because it just depends on your band gap. The topology creates a large band gap and a wave can only go in one direction. So there are some advantages from a practical standpoint as well, but that's different. I hope I've been able to give you a kind of an idea of a physical picture of what's happening.
I don't want to take anybody else's time, but you've given me the consequences of your theory, but you still haven't taught me the origin of the theory. What causes this?
This is a series of 10 papers, right? So that
charges accelerating the radiator. I understand. Okay.
Right.
Here, why, if I have an electric field and magnetic field, then I have a whole conductivity. Why does that produce some special epsilon or susceptibility that causes this thing? Yeah, I still don't understand, but maybe we can talk about
I'll be very happy to discuss in a lot more detail. Yes. No, that's a great question. I completely agree.
I was just wondering, so for the ND part that you talked about?
Yes.
So in that case, was the spin angular momentum, was that just regular circularly polarized light?
Absolutely. So in this case, this was just our first experiment. And we had basically just the most basic detuned laser, which is circularly polarized.
Yeah, what wavelength was that?
This was, I have to look at it more carefully, like believe 800 nanometers. And we've also done a wavelength dependent study in a follow-up paper.
So is this what you might call like the optical Stark effect or the AC Stark effect?
It is the AC Stark effect, which is actually proportional. You can show that the AC Stark effect is proportional to the spin density of light locally at the position.
So you're saying that maybe you could use other more interesting kinds of spin polarized photonic fields.
Yes.
And do similar.
Exactly. Also in an NV for a lattice and so forth. Yeah. Now, there's one thing that is going on in the theory, and I'm happy to discuss in more detail. Our wavelength dependence of this effect does not agree directly with the AC Stark shift. So that's something we are trying to study in more detail about why does it not agree, and is there something else happening beyond the Stark shift? But I would say that once we do things more carefully, both the theory and experiment, it should come down to the same scaling with frequency as well as the same scaling with power as the AC Stark shift. Yeah.
Sorry, when you were doing the 1-point compactification of the milliwinsel, so beside it, you were compactifying the frequencies as well.
Yes.
Didn't get that.
Okay, great. That's a very good and technical question. Let me kind of explain this. So one thing which is very important is that in the case of the hydrodynamic fluid, the electron-electron interaction, there's actually no Brunel zone because we are looking at the continuum limit. So think of it this way, that there's no lattice. It's a continuum fluid. That means you only have the origin, like zero momentum, and you have very, very large momentum. There's no periodicity in the lattice in this theory. So that makes actually the topology way more complex to define because you don't have a donut. And so where does that compact manifold come from? It actually comes from the fact that the Hall viscosity causes the response functions at these large values to actually have very similar decays that allows you to actually close this entire thing into a one-point compactification.
All responses on the
Yes.
Those have like a pure gauge.
Yes, it does. Exactly. So now you can actually compact this, but this is only in momentum space. Now remember that we are talking about the electrodynamic waves inside here. So it's very different from the electron wave function, which does not have a energy dependence explicitly. The wave function can be just once you have the Brunel, you just look at the wave function at a certain energy. So now you also need to look at not just the two-dimensional compactification of momentum space, but you have the frequency space that also should be compactified.
Is that like a Matsubara?
Yes, it is. Absolutely. So this is why this is the I here. These are the Matsubara frequencies. Now you have plus I infinity and minus I infinity. So this is actually an open manifold. But what is interesting, and this is the part we proved in the paper, that because of Kramer's chronic relationships and the F sum rule, this actually compactifies to a circle. And now on this manifold, you can define topological indicators.
I have a question on the Hall viscosity term. So you have a attractive and a repulsive term. So are there like two terms like competing with each other so that the parameter you can tune it from positive to negative? So I didn't catch the expression.
So this is the part I have to say is still under investigation. We are still looking at when do you get attractive Hall viscosity, when do you get repulsive, how do you tune it? So these are things that we are still exploring. I don't have a concrete answer for this. The only thing that we do know And that comes out of the theory is that for attractive Hall viscosity, as well as no Hall viscosity, all those cases, this is the region. And only for the case of repulsive Hall viscosity, we have this interesting phenomenon. So that's something that really comes out of the theory. And so we are focusing a lot on this regime. Yeah.
More questions? If not, please join me in thanking. Oh,
I had a question.
Oh, yes,
So
sorry.
the slide where you're showing, I think it was photonics, the dispersion spectrum.
Yeah.
Where you apply from the silicon.
Yes.
And you're predicting that tail. Do you have experimental predictions?
No, not yet. Not yet. We're working on it. We have to think very hard about what experiments can actually probe this.
Right.
It'll take some time. Yeah. So I do not have a direct experiment because of multiple reasons. One is that we are really looking at sub-nanometer variations of the electrodynamic field. And the second thing is the absorption in the ray, anything above the band gap, there will be absorption. And these waves will also be very, very sensitive to absorption. The interband transitions will be damped. So we are still thinking hard about what can be done.
One more really quick. I think it was the slide that you were just on where you mentioned N variant.
Yes.
And you said it works well for graphene, but it doesn't work well for other materials.
No. So I would say that that's the no. So I would say that the NN variant we believe is non-zero in graphene with a Hall viscosity. There definitely is going to be many other materials in which this would be non-zero. We still have to search for it. But the crucial ingredient is repulsive Hall viscosity.
Okay.
It doesn't matter which material. If it has repulsive Hall viscosity, the N will be 2. That's what we mean by topological. It's really does not depend a lot on the microscopic details. Some aspects of the theory govern what phase of matter it is in.
okay.
Thank
I
you.
have
Everyone.
several questions, but we can have time to talk.
All right.
Okay, thank you very much. Thank you. It was fantastic.
Okay, thank you.